The first element that we're going to look at are our fault current limiter. This is our fault current limiter. The problem type is an axisymmetric problem. So we have an axisymmetric problem. The frequency, it's AC magnetic, so the frequency is 60 hertz, as well as we have a coupled electric circuit here. And I'll go over each one of these elements. In this case, this is the air region. So for the air region, we give it a relative permeability of 1. This is the primary coil. The primary coil is copper, so we give conductivity of copper. It has a relative permeability of 1, as well as each one of these circuit elements, roughly 99, are connected in series. So each one of these is in a series connection. And then we have a secondary coil. The secondary coil also has the conductivity of copper. Once again, these are in series, so it's identical to the primary coil, except it simply has a smaller diameter. Okay, and in this simulation, I wanted to illustrate the superconducting boundary is simply an edge with 0 magnetic vector potential. Okay, and then the sides of the model, I'm giving 0 vector potential for the sides of the model, and we would like to really extend these out so it doesn't influence the field here. So these are probably going to be should be a little bit farther out. Now, I'm going to look at the solution. This is a solution for the case where the tube is superconducting here. So we have current flowing through the primary coil, and if we want to look at the current flowing through the primary coil, I have a coupled circuit to the model. This is our coupled circuit, so that the primary coil is excited with 120 volt excitation. Okay. Now the secondary coil is connected to a capacitor, and this capacitance value is chosen such that the resonant frequency is going to be close to 60 hertz. And we can actually use the label mover feature to find the capacitance that's going to give us the maximum attenuation of the fault current. So, but for right now, we have this, the superconducting tube is screening the secondary circuit here from the primary field. Now, under fault condition, the superconducting tube would go normal, and I want to demonstrate that. So I'm going to take the boundary of the superconductor, and I'm going to make it with no boundary condition. Then if we solve this problem, we should have field at the location of the secondary coil, and that's going to reduce the current that's flowing in our primary circuit here. Okay, this has been solved. Okay, if we look at the field plot, that this would correspond to where the tube is no longer superconducting. And now if I look at my current element, okay, the current that's flowing in the primary circuit here is 36 amperes. Okay, this is under the fault condition where the tube is normal here. Okay, as well we can look at the current that's flowing in the secondary circuit. So we can see there's a very large current that's flowing in the secondary circuit here. Okay, well I wanted to compare the current in the primary under the fault condition to the current in the primary where there's no fault. So I'm going to go back and reestablish this. We should have looked at this the first time, but do that. So in subsequent models, we're going to be, instead of just a a secondary coil, we're going to also look at ferrite element. We can put ferrite elements in here. Okay. Now, I want to look at the current that's flowing in the primary. It's roughly 500 amperes. So in this case, this was a pretty effective design. It's not optimized in any way here. We're just illustrating the capabilities of using QuickField to design the fault current limiter for the moment.